This is Algebra 2 with trig. Working on Unit 1C, we will be solving quadratics by factoring. Okay, one of the things that we notice here is that you can use factoring to solve certain quadratic equations. A quadratic equation in one variable can be written in the form of y equals ax squared plus bx plus c. This is known as standard form. The X-Intercepts of a quadratic equation are called the solutions of the equation. So you know about X-intercepts. That's where the graph crosses the x-axis, and those x values are solutions of the equation. So when we're talking about solving a quadratic, we're looking for where the graph crosses the x-axis. If the left side of your equation can be factored, then the equation can be solved using the zero product property. So with the zero product property, we're going to take our equation, if it's written in our parentheses already, kind of in a factored form, or what we like to call intercept form, equals 0, we can set the two equations equal to 0. If A and B, you have your binomial of A and your binomial of B. If A and B are expressions, and A times B equals 0, so you're thinking about two numbers that multiply to be 0. What do you know about those two numbers? One of them has to be 0. Either A is 0 or B is 0. So here we have the quadratic. It's written in intercept form, and we set the A factor to 0 and set the B factor to 0, and you solve, and that's how we got our value of x. -5 or a -2 will make this equation equal to 0. So one word that means the same thing is called roots. Find the roots of each equation. Well, we're going to work towards factoring that. So when we talk about factoring an equation, we're going to break it up into the two multiples that are make it. Like we learned yesterday, we could use the guess and check format, where two numbers that multiply to be your first term and two numbers that multiply to be your last term that add to be your B term. Two numbers that multiply to be -15 and add to be -5 or -2 is -5 and a +3. So that's factored. Now once it's factored, we're going to set each one of those equal to 0. So I get x equals 5, and x plus 3 equals 0, so I get x equals -3. This should be a t. We want the variables to match. So you have t squared plus 8t minus 20. Well, we can try to set that equal to 0. We're going to factor it. So we know that our first terms are both going to be t to get us t squared. We need two numbers that multiply to be -20 but add to be 8. What would those numbers be? 4 and 2 multiply to be 8, but that doesn't multiply to be 20. We need two numbers that multiply to be 20. 2 and 10. But it's got to multiply to be a -20. So it's got to be a -2 and a +10. Those two numbers will add to be +t, 8t, and multiply to be -20. So then we can set them both equal to 0. So t equals 2 and t equals negative 10. Here we're going to factor it apart. We're looking for two values that multiply to be 32 and add to be negative 12. Remember the tables we have talked about before. There's multiple ways for us to multiply to be 32. You can make a table and remember our sum and product. So we want a product of 32. So 1 and 32, 2 and 16, 4 and 8. Those are our different ways that we can multiply to be 32. Well, this way adds up to be 33. This way adds up to be 8. This one adds up to be 12. But this is a positive 12. If they were both negative, it would still multiply to be negative 32 and add to be negative 12. So they both need to be negative, but still the only one that works is negative 4 and negative 8. Some of you may have recognized that already. So we're going to set them both equal to 0. Add the 4 across, add the 8 across, and we've come up with our two answers that make our expression, or this equation, true. It makes it equal to 0. 16, if we plugged in the 4, we'd have 4 times 4 is 16, minus 48, and then we have the additional 32, and that brings us up to 0. So we could look here at a graph. Remember, you can check your answer by using the graphing calculator and locating the x-intercepts. So if you typed in your equation, either in standard form or in factored form, factor would help you the most because that would help you check your answer. But anyway, you could see if they are indeed crossing at 4 and 8. This graph was of something else. So if you type in your standard form into your y equals of your graphing calculator, you'll be able to see what your x-intercepts are. Okay, so here we're talking about what are the roots, or what are the zeros is another way of saying it. So we can say x squared plus 2x. We would subtract a 35 across because we know it has to equal 0. It can't equal 35. We need two numbers to multiply each other that multiply to be negative 35 and add to be 2. To get x squared, FOIL would require it to be x and x, and then we need two numbers, so we'll use 7 and 5. It's got to be more positives than negatives because it's adding to be a positive 2. So x minus 5 equals 0. Add the 5 across. X plus 7 equals 0. X equals negative 7. Those would be considered the roots of your equation. Here we're using a different variable, but it's still the same concept. So this is an equation because it equals a value. We're glad that it equals 0 because we need our quadratic to have, if we have an x squared, or in this case h squared, if we have an h squared and another h, then everything has to be on the same side of the equal sign. Now we can factor it apart. We'll use h and h. What two numbers multiply to be 1 and add to be negative 2? Be sure you're thinking about these. But it would be negative 1 and negative 1. That multiplies to be positive 1. That adds to be negative 2. So you can set your two equations to 0, and you'll see that you get h is 1 and h is 1. So they're the same answer. Neither one is considered extraneous. The only answer is when h is 1. So this would have a vertex on the x-axis, or h-axis in this case, where the value of h was 1. So here we should have it equal to 0. So we have b times b, that's what gives us our first term. What multiplies to be negative 10 and adds to be positive 3. Five and 2. We need more positives because it's a positive 3. And they have to multiply to be negative 10, so the signs have to be different. So b plus 5 equals 0, and b minus 2 equals 0. So subtract your 5 across, add your 2 across, and we found the two zeros, or in this case, what we like to call them, the two roots of the equation. What are the roots of the equation? Zeros of a function, same idea, just another way of phrasing it. The x-intercepts of the graph of y equals a, x minus p, x minus q, the x-intercepts are p and q. Because the function's value is 0, when x minus p equals 0 and x minus q equals 0, the numbers p and q are considered zeros of the function. So, just another way of asking the same questions. What are the zeros of these functions? And we find that by turning it into X-intercept form. So can you turn this quadratic, the standard form, into intercept form? You can pause the video and go ahead and work on these three. They're very similar to the ones we did earlier, and see if you can factor those apart, putting them into X-intercept or into intercept form, otherwise known as factoring. So we will look to see what multiplies to be x, what multiplies to be negative 28 and adds to be 3, that is 7 and 4. We know we need more positives because the 3 is positive. We're going to have less negatives and more positives. So we're going to set our two binomials equal to 0 using the zero product property. And we get x equals negative 7 and x equals 4. We know our first two terms are going to be x squared. We're going to have a negative 2 and negative 2. That multiplies to be our negative 4 and adds to be, that multiplies to be a positive 4, and that adds to be a negative 4. You can call this one a perfect square trinomial because it's made up of the same binomial twice. So this graph crosses the x-axis at only one spot, where x is 2. That means the vertex is exactly on the x-axis. It's been translated 2 to the right. This looks like another perfect square trinomial. When you multiply, if you can take the square root of the first term and the square root of the last term, So that's 5 and an x, so 5x. And the middle term is twice as much than that 5x, which is 10x. Then you know you have a perfect square trinomial. What multiplies to be positive 25 and adds to be negative 10? It's a perfect square. It's the same term written twice. So we have factored. We have found the zeros. We have found the roots. These are all considered X-intercepts of the quadratic. Solutions to a quadratic equation can be referred to as X-intercepts, and they are also known as zeros and roots of the quadratic function. Like we've talked about before, if you have this A or B expression, two terms that multiply each other, and A times B equals 0, it has to equal 0. If it equals 1, there's multiple ways to multiply to be 1. But we need it to multiply to be 0. Either A is 0 or the B is 0. So you go ahead and try factoring out these bottom ones. Oh, look at this one. What multiplies to be 1 but adds to be 1? Nothing does. So this would be called prime. It's not factorable. This quadratic is considered prime because it's not factorable. What multiplies to be 20 and adds to be 9? 5 and 4 multiply to be 20 and add to be 9. When you FOIL this together all the way, x times x gives you x squared. X times 5 gives us 5x. 4 times x gives us 4x. And 4 times 5 gives us 20. We can check our work by multiplying this through. You'll see that it matches. So when x plus 4 times x plus 5, that gives us the factors of x squared plus 9 plus 20. 9x plus 20. So we're just factoring. We're not solving because it just says factor. We know because the leading coefficient is a 1 that we're just using x's. It's not a 3x or a 5x or anything like that. It's just x times x that gives us x squared. We need a 15 and a 3 because that multiplies to be 45. But what adds to be negative 12? Negative 15 and a positive 3. There's only one way for us to multiply to be 45 and add to be 12. Negative 45 and a negative 12. If we're going to talk about the roots, then it wants us to solve, and it wants us to know the specific values of x. Notice that we have an x squared and we have a normal x. In those situations, we need to bring all the terms to the same side of the equal sign. If you have two different types of x's, then you need to bring everything to the same side of the equal sign. X squared, add your 2x over, subtract your 8 over. Now it equals 0 on the other side. So it has to be x and x, 4 and 2. We know that it adds to be positive 2, but multiplies to be negative 8. We're going to have more positives than negatives. and then we can set those equal to 0. And those would be considered the roots of the function. Here, this should equal 0. And we're going to have x squared. Well, that's what the equation is. Well, let's put in our parentheses and think about what multiplies our two binomials together. X and x gives us our x squared. The last two terms would have to multiply to be negative 32. And when we do the FOIL, the outer and the inner, that's what adds together to be the middle term, the b term. So we have 8 and 4. That multiplies to be 32. One of those numbers has to be negative. A negative 8 will help us add up to become a negative 4. Positive 4 multiplies out to be negative 32 and adds to be a negative 4. We do the zero product property, and we see that our roots are going to be negative 4 and 8. When you're solving for roots, or the zeros of a function, you need to be sure to have an equal sign involved. So that was why I knew an equal sign had to be here. In other problems, like up here, there is no equal sign. We don't solve for anything. We just might factor. We might write it in a different format, but it's still the same equation. And if it's not breakdownable at all, it's called prime. Okay, find the values of x. So what are the x values that make the function equal to 0? Well, these are the numbers that made this function equal to 0. So we need to factor and do the zero product property. So here we're going to factor and do the zero product property. So 6 and 2, no, that multiplies to be 12 and adds to be 8. What multiplies to be 8 and adds to be 12? 8 and 1 multiplies, so if you made a table, remember our sum and product table, to become a sum of 12 and a product of 8. 1 and 8, 2 and 4, those are the only ways. So this, there are no x values. So that would be considered no solutions. Let's try this one. Now here we don't have that middle term. We have x squared and we have 0 x's minus 25 equals 0. We don't have a middle term. So in that case, we want two numbers that multiply to be 25 and add to be 0. It happens to be pretty easy because that's positive 5 and negative 5. So when we set those equal to 0, we see that we get negative 5 as an answer and positive 5 as an answer. Those are your two x values that make the function equal 0. Now we're going to look at a story problem. You have a rectangular vegetable garden in your backyard that measures 15 feet by 10 feet. So we have 10 feet going one way. We have 15 feet going the other. This area equals 150. You want to double the area of the garden by adding the same distance x to the length and the width of the garden. So we're going to add a number to the 10. We're also going to add a number to the 15. So if we add 2 to both of them, like 12 and 17, what does that multiply to be? Well, we want it to multiply up to become twice as much as the current area. So we're going to take the 10 and add a number to it. We're going to take the 15 and add a number to it. And we want that to be twice as big as 150. So we could rewrite that if we wanted to. X plus 10, X plus 15. We're usually more familiar with it in that format. We want that to equal 300. So there's multiple ways we can do this. We can FOIL this out, make one big quadratic equation, and then solve the whole thing by hand. Completely works. We could take this quadratic equation and find out where it equals 300. We could take our graphing calculator and go to y equals and type in our equation of x plus 10, x plus 15. We want to know where this equation equals 300. If we go to the table, we can find out that 300 for x, right? Before we add anything, we knew the area was 150. And if we add 1 to the 10 and 1 to the 15, so if we do 11 times 16, we get 176. If we add 5 to both of the numbers, 5 to the 10 and 5 to the 15, so we take 15 and 20, that gets us to 300. That's what we wanted. So that was one way to do it. We knew we wanted to check out 300, so we could have gone to our maximum value, our window, our maximum y value up to 400. Remember, we're going to have an x-intercept of our quadratic at -10 and also at -15. So it's going to curve all the way through our parabola. And we have this line over here at 300. Let me show you. If we took our x minimum way out to -30, you would see the rest of the parabola. It crosses here at -15, it crosses here at -10, and this is the portion we were seeing earlier. Anyway, if we go to calculate and look for the intercepts, this is our first equation. Here, it doesn't matter where I'm at on the equation, I hit enter. Is this my second equation? Is this my second curve? The answer is yes. Now there's two answers, but we only want the positive x answer. So I need to be sure my cursor is closer to the positive than it is to the negative. And you'll see that when x is 5, we get the value of 300. Using the calculator, 5, 300 is the solution. So find the x value in the new dimensions. X would have to equal 5, and we would have 15 plus 5, which is 20, times 10 plus 5, which is 15. That would give us our 300. So it would be 20 by 15 feet. Those are the new dimensions. Let's take a look at this one. This one we're supposed to find the value of x. If we know the area is supposed to be 16 meters square meters, then we know that we have x and 3x plus 2 equals 16. Well, this looks a little bit different. It doesn't have two sets of parentheses. But when we multiply this out, we get 3x squared plus 2x equals 16. So now we have this quadratic. It has an a value that's bigger than 1. That's a little tougher to be able to factor. So we'll hold off from that at the moment, and we'll talk about different ways to solve this. One way would be with our calculator. We have our 3x squared plus 2x minus 16. And we know, or we're under the impression, I'm going to zoom 6 because I want to go back to the normal window, the 10 by 10. So it looks like it goes down pretty low. If you wanted to look down lower, we have a minimum value. And you can see I just kind of guessed at a y value, and it went down lower, and now we can see the full parabola. We're looking for two different answers. Only one answer makes sense in our problem because we can't have a negative type feat in our story problem. So you could say second trace, which gives us the 0 of the function, and that's when it says left bound, right bound. So there's a left bound, there's a right bound, just like we practiced before. Guess means, do you have more than one answer inside that small window? No. So our answer is 2. When x is 2, we're at 0. Another way to do that is to look at the table. We get 0 when x was 2. You would also get 0. Oh, it must have been between values. But it was a negative number. That can't be the dimensions of our rectangle anyway. So when x is 2, we get 0. That would be the value of x. Okay, like a problem we've solved in the past. An internet provider sells internet service for $300 per month to 1,500 customers. For each $1 increase of price, the number of customers will decrease by 25. How much should the company charge in order to maximize revenue? So, we're going to take our revenue, remember, is price times the number of items. In this case, it's price times customers. And our current price is $30, and our customers is $1,500. That's our revenue. And our revenue is going to be 30 times 1,500. So we get 45,000. And then we learn that if we take our 30 and subtract $1 from it, and take our 1,500, well, that was add, right? We increase the price. So that's adding by 1. We're going to decrease the customers, decrease by 25. So when we do that, if we take our 30 and add $1, take our 1,500 and subtract 25, we get even a higher profit. And we can see if we do that again, if we add 2 times the 1, and 25 times 2. So if we take our 30 and add the $1 2 times now, then we're going to take the 1500 and subtract the 25 2 different times. And that gives us even a higher profit, 64,400 or 46,400. So now you can see the equation being developed. 30 plus, it's $1 times 2. Or, sorry, it's $1 times X. So 30 plus X. Let me say that one more time. That's 30 plus the $1 times the number of opportunities that we have to increase it, which is our X, and our 1500 minus the customers, 25 of them at a time for every X, for every increase. So that's what we're going to put into our Y equals. We take our 30 plus our X, our 1500 minus our 25X. We can type this into Y1 of our graphing calculator. We can look at the table to see when do we maximize our revenue. Well, we knew from the beginning we had 45,000. And it builds up to 48, 49, 50,000, still increasing. Up now it looks like it's decreasing. So the highest number that we got to was 50,625, and that was at 15 when we changed the number by 15. How much should the company charge in order to maximize revenue? We're going to add $15, so that's $45 is what we should charge. What is the monthly revenue? Well, we take our 30, add our 15, take our 1500 minus 25 times 15, and our maximum revenue. Remember, that's what the table told us. The table showed us 50,625. When we plugged in the numbers to our equation, we got the same result. Our maximum revenue was 50,625 per month.